Okay, so let's get started. We're going to demonstrate what happens for a nonlinear transformation when the data record is large. Okay, so um, to see why this property holds, we return to the previous example of estimating a squared by x bar squared. Although x bar squared is biased, we notice from 3.18 that a squared x bar squared is asymptotically unbiased or unbiased as n approaches infinity. Furthermore, since x bar is distributed by this n a uh, sigma squared over n, we can evaluate the variance. So you take the variance of x bar squared, which is equal to effect of x bar to the 4 minus e squared x bar squared. By using the result that if c is distributed n, then effect of this is this. This is what? This is Gaussian with mu and sigma square. Right? So if c is square, this is called the second moment, if you will. That'll be second moment. But anyway, it's a terminology, but it can be proven. It's just using the basic properties from probability. So you take the expectation of c squared, which is equal to mu squared plus sigma squared. If you take it to the fourth, then that would be mu to the fourth plus 6 mu squared sigma squared plus 3 sigma 4. And therefore, variance of c squared is equal to variance to expect of c to the 4 minus expect of c squared. And this thing is the square of this, so we have it. And this thing is here, so we just put this here, and do some simplification. We get variance of c squared. But the point is, the derivation, of course, takes some mathematical reformulation and simplifications, but it all uses the basic property of probability. So if it's not familiar with you, you can check some identities in the basic probability. And anyway, that we at the end we are going to get variance of this. For our problem, then we have variance of x bar squared equal to 4a squared sigma squared over n. How come? How come? Because uh, because we are using this equation, and x bar is what? X bar is in the row of c here, and c is in the row of Gaussian distribution mu and sigma square. And you can check x bar. X bar actually has zero mean and sigma square over n, right? So you put this as zero mean and sigma square over n, and you put the corresponding parameters into here, do some simplification, you get something like that. But in the row of sigma square a and n. Okay, so that's how we get this x bar. Just think of x bar as c here, and then you do the process one more time, then you get this. So, but the point is, as n goes larger and larger, this term sustains, but this term has n squared, right? This term, when it's n squared, it goes larger and larger, and its speed of increase is a lot faster than this because it's square. It's square. Let's say you have 100, then this will be this will be 100 squared, which is 10 to the 4, right? If this is 1,000, this is will be 10 to the 6. That's a large number. So this person disappears very fast. As a result, we will say the variance approaches this term because this disappear very fast. The last term in this covering the to 0 faster than the first. But this is just the CRB. Our assertion that this is asymptotically efficient is verified, right? Because it, at the end, we are going to approach this end, but this is the CRB. This is the ordinary CRB. So if n is large enough, then this will be good enough because it approaches the CRB. Okay, so I think we have some properties here. Okay, then the next thing is extension to a vector parameter. So we now extend the results of the previous section to a case where we wish to estimate a vector parameter theta. We'll assume that the estimator is unbiased. So unbiased, then the vector parameter will allow us to place a bound on the variance of each element. Notice it's not, we cannot compare and say which vector is larger than which, right? That would be that would be unreasonable, right? The comparison can only be done on a scalar. It cannot be done uh, on a vector, right? So we will say that we want to place the bound on element because element is a scalar. Is a scalar. Let us derive, which we skip. The CRB is found ith element of the inverse of a matrix. So if you take the Fisher information matrix, you take the inverse, and its ii element would be the lower bound for theta I. I'll repeat one more time. You take the Fisher information matrix, you take the inverse, and you take the ii element. Ii element means, let's say if you have something like this, this is 1, 1, 2, 2, 3, 3, 4, 4, right? So ii is a diagonal element at the ith location. Okay. So then the Fisher information matrix is defined this way. I of theta, and we define its ij element because we want to define each element for the matrix. Then once all the elements are defined, then the matrix is defined. So ij is expect partial log px theta. This is the original likelihood function. But partial theta I, partial theta j. Originally, we are partialing for 2 times for the same parameter, right? Recall we have partial theta squared here. That's only for one single parameter. Now we have a lot of parameters. So at the ij's location, you have to partial theta I and then partial theta j. That would be better, right? That would be better. That would be reasonable, so to speak. And then you take the expectation, take the minus, that's the same as before. And for I all the way to P and J all the way to P, so each element in Ij will be defined. Then you take the inverse function. Notice that this is not reciprocal. It's an inverse function, and you take II. Instead of taking the element out and take the reciprocal. That's not right. That's not right. Okay, so then in evaluating this, the true value of theta is used. So as an example, I think I can go a little bit faster. DC level in white Gaussian noise. But chapter 3 is sort of a very important part of estimation problem because that's sort of core 核心。第3章是核心。Chapter 3 is sort of the core of estimation theory because it builds up a lot of fundamental concepts and also it gives you simple examples to illustrate those concepts, formulations, and bounds, low bounds, CRBs, and unbiasedness, things like that. Those are actually very fundamental and very core for this. And later on, we have other approaches than examples. They are still important, but this is the most fundamental. Chapter 3. Okay, so we will extend this to the case where, in addition to A, the noise variance sigma square is unknown, right? So now we have two parameters, so that's called vector parameter. Let's go back a little bit, a vector parameter. If we have a vector parameter, what that means is we have multiple parameters. We just put it in the vector form. So we now extend example to a case where, in addition to A, the noise variance is also unknown. The parameter vector is then a vector A sigma square T, and hence P is equal to 2. The 2 by 2 visual information matrix. Recall this? I want you to just take a look at this one more time. Partial theta I, partial theta j. Right? And this is 1, 1. So the first parameter is A. So you partial square lnp, partial A square, expect minus. Here is easy. Partial square ln, then partial sigma square twice, expect minus. So that's good. That's good. This is also good. And here we have some tricks here. You have theta I and j. You have partial A and partial sigma square because this is theta 1 and theta 2. And so you have second order derivative and then partial A, partial theta sigma square. Here it's the same thing. You have partial sigma square, partial A. Now you have diagonal and off diagonal. Okay, so it is clear from 3 to 1 that the matrix is symmetric since the order of partial may be interchanged. This can be interchanged. So they are symmetric and they can be shown to be positive definite. I think this is a property. Recall linear algebra. Positive definite means that its eigenvalues, all its eigenvalues are positive. That's called positive definite. If positive semi-definite, then it's positive or 0. But here we have positive definite. Okay, so the log likelihood function then can be written this way. Ln p x theta px theta is equal to this. How come we recall this is log likelihood? You write it into what? You write it into Gaussian distribution and then take log. Not a big deal. And then you have log, which is what? Which is the numerator here, 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 and here. And then the derivative are easily found as you take the first order derivative partial A, first order derivative with respect to sigma square. Right? This is taken for A. This is taken for sigma square. Then what? you want to do the second time, you do this the second time. So you do this with respect to A, you get this. And then you want to get A, partial A and partial sigma square. So what do? You take this, you do it with respect to partial A, and you get this, right? And then you want to get partial sigma square twice. So you take this, you do it with respect to sigma square one more time, you get this. So now we have what? We have this, right here. We have this and this here. We have this term here because it's second order twice here. So we have every term in the feature information matrix in here. Okay, then now we are happy we have every term with us. And then we take the negative expectation. This is as required by this, negative and expectation. But when you take the expectation, you see, you take the expectation of this xn, you take the expectation is a minus a is 0. So you take the expectation this is 0. You take the expectation this is 0. Then you get this only and this only. So as a result, you take the expectation, you get something like this. Of course, you put minus sign, you get here. Now you have variance A equal to feature information matrix. You take the inverse, you take the diagonal element. And what happens here is, this is the diagonal matrix. So when you take the inverse, it's easy. You just take the inverse of the diagonal element. So 1 over sigma square becomes reversed sigma square over n, right? Sigma square over n over 2 sigma to the 4 reversed becomes 2 sigma to the 4 over n. So variance this over this, variance this over this. Then we're happy. You get a vector version. You get a vector version. Come back again. Originally, we only have unknown as a. Now we have unknown a and sigma square. It becomes a vector, which looks difficult, right? At the beginning, it looks difficult because suddenly we have two parameters. But now we'll be able to get a bound for the two parameters by using this. So now we have sigma square over n, 2 sigma to the 4 over n. Now we have variance of this and variance of this. This is a CRB. Okay, I think we go up to this point and take a break and then come back soon.